Hi everybody. Okay, so in our last video we were talking about how to determine limiting reactants in using particulate diagrams, but that's not super practical, right? Because we can't shrink down to the size of atoms and count all of our atoms. So instead, what chemists do in the lab is they start out with the masses of the reactants that they have, and then they do some math on it to figure out which one's going to run out first. So that's what we're going to learn how to do in this video. So what you have to first ask yourself every time you're going into one of these stoichiometry problems now is this a limiting reactant problem? So let's read this equation first. Carbon and sulfur react according to the balance equation below. If 26.56 grams of carbon and 31.25 grams of sulfur are added to a reaction flask, how many grams of carbon disulfide will be produced? Assume the reaction goes to completion. So what that last sentence means is we are assuming that one of our reactants, or all of our reactants maybe, are going to get completely used up. This reaction will happen. It'll go all the way. Something's going to get used up. But to decide if it's a limiting reactant problem, you have to ask yourself one question. Does the problem provide measurements for more than one reactant? If the answer is yes, then no matter what, it is a limiting reactant problem. You have to go through the limiting reactant steps. If the answer is no, then you can assume that your other reactant is in excess, and you can just complete the problem using regular old dimensional analysis. Obviously, because this is in our limiting reactant section of the notes, this is a limiting reactant problem. And if we go back and double check, 26.56 grams of carbon is one measurement that I gave you. That's one of our reactants. And then I gave you 31.25 grams of sulfur. That's our other reactant. So I gave you measurements for both of our reactants. That means that yes, this is a limiting reactant problem. So to start yourself off, you're going to get organized. You want to make sure that you list your values of each reactant under the reactant in the reaction equation. Just helps you make sure that you know exactly what you have and what you are asked to find. So in this problem, I know that I have 26.56 grams of carbon and I have 31.25 grams of sulfur. At the end of the problem, I am asked to find grams of carbon disulfide. So I'm going to put a little question mark with grams under that right there to tell me that's what I'm trying to solve for. Step 2, if necessary, convert reactant measurements to moles. It's not practical for us to measure or to compare masses of different species. If you have an insane amount of hydrogen, that doesn't really necessarily mean that hydrogen is not going to be the one to run out first, because hydrogen also has a super, super, super light molar mass. So you can't compare masses of different species. Your first step after getting organized is to make sure that you have everything in terms of moles. We can compare moles because our balanced chemical equation gives us mole ratios. So we have to convert our carbon measurement and our sulfur measurement to moles. Let's start out with carbon. So we're starting out with 26.56 grams of carbon. At the end of this, we need to end up with moles. So what is the conversion factor that takes us between moles and mass? It's molar mass. So to set this thing up, we want to make sure that our grams of carbon cancel out. That needs to go in the denominator, which means that our moles of carbon need to go in the numerator. Recall, molar mass is defined as the mass in grams per 1 mole of every substance. So you have to have your moles, your mole coefficient be 1 here. So we have 1 mole of carbon. This is just elemental carbon, so we just have to look on the periodic table and find that it's 12.011 grams of carbon per every 1 mole. If we just double check that our units are going to cancel out, grams cancel with grams, I'm left with moles of carbon, which is exactly what I wanted. I plug this into my calculator, and you end up with 2.2113 moles of carbon. Remember that when you're finding your molar masses, you want to make sure that you keep all your decimals, because you want to keep your answer as accurate as possible until the very end. All right, moving on, sulfur. Okay, so I'm starting out with 31.25 grams of sulfur here. Again, I want to convert to moles, so my setup is going to be the exact same. I need 1 mole of sulfur in the numerator. Elemental sulfur means I can just look at the periodic table and find that elemental sulfur's molar mass is 32.06 grams of sulfur per 1 mole. So at the end, I'm going to end up with moles of sulfur. Just double check that my units work out by cross-canceling. That looks good. plug it into my calculator, and I end up with 0.9747 moles of sulfur. So now I can deal with comparing these things because they're both in moles, and I have my balanced chemical equation in which I know the mole ratios. So from here, I can now start identifying the limiting reactant. I can compare these values of moles to each other. So I am going to start this out by thinking about how many moles do I have versus how many do I need in the balanced chemical reaction equation. So notes for this one, what's the mole ratio? If the mole ratio is not 1-to-1, you have to compare the amount of moles that you have by dividing your given moles by mole coefficients. So if I look back up at my balanced chemical equation right here, I have 1 mole of carbon per every 2 moles of sulfur, not 1-to-1, therefore I got to do that division. So let's start out with carbon. I know that in this problem, I have 2.2113 moles of carbon. From the balanced chemical equation, I know that I only need 1 mole of carbon in this reaction, so I would just divide by 1 mole of carbon. Looking good there. Okay, now let's do the same thing for sulfur. In this problem, I have 0.9747 moles of sulfur. From the balanced chemical equation, I know that I need 2, so I'm dividing this by 2 moles of sulfur from my reaction. So when I plug this into my calculator, or do this in this first one in my head, 2.2133 moles of carbon versus 0.48735 moles of sulfur. So what I have to look for now is which one's smaller. Whichever one is smaller means that's the one that's going to run out first. So I only have this much sulfur. This is clearly the smaller number. So because I have a smaller amount of sulfur and a smaller ratio of sulfur in the balanced chemical equation, this means that sulfur is equal to my limiting reactant. Okay, so sulfur is our limiting reactant, which is good. Now we know that sulfur is going to run out first. That's information we can use to help us figure out the rest of the masses of reactants that the rest of the masses of the reactants that I'm going to have left over in the form of carbon, and how much product, carbon disulfide, I can make when this reaction goes to completion. So here's what we're going to do now. We're going to construct what's called a BCA table. BCA just stands for before, change, and after. The reason why I'm showing you this method is because you can use a BCA table to calculate the amount of all species in your reaction before the reaction happens, while it's changing, and after the reaction occurs. I will say the before, change, after table is a lot of work if I'm just asking you for one species in a problem. So I will show you another method in class for how to shorten this up, but this method does work all the time. So this is the one that I'm going to show you, even though it is the longer one that does require a little bit more work. So first step to setting up a BCA table, you want to rewrite your reaction equation. So I have carbon. I have carbon plus 2 sulfurs yields excuse me, carbon disulfide. Okay, I'm going to set myself up a section to write about the before, the change, and the after. Good Lord. Okay, so before my reaction occurs, let's think about how many moles of each substance I have. Before, change, after, you can only put things in terms of moles, no masses. That's why we converted to moles in the first place. So before my reaction occurs, I know that I have this many moles of carbon because I calculated it out already. So I have 2.2113 moles of carbon. Sulfur, when I begin, I have this many moles because, again, we calculated it out ahead of time. I'm starting with 31.25 grams, so it means I'm also starting out with 0.9747 moles. Same thing, just different units. Okay, how many moles of product do I have before the reaction occurs? Hopefully you shouted 0, none. We shouldn't have any product before the reaction happens. That's impossible. So that's going to get a big fat 0 right there. All right, next up. What's going to happen during the reaction? So we're representing the gain of product and the loss of reactant through positive and negative signs. But how much are we gaining or losing? It's dependent upon the mole ratios. So carbon, I need 1 mole of carbon to react with 2 moles of sulfur. So every time this reaction happens, I lose 1 mole of carbon. I lose some amount of carbon. At the same time, I'm also losing 2 moles of sulfur according to the balanced chemical reaction equation. So that's getting represented like that. And how much product am I gaining at the end? Well, I'm gaining plus 1 mole of product every time this happens. So after the reaction occurs, what this means is I had 0.9747 moles of sulfur. I've lost what we're calling 2x amount, but I know that this is my limiting reactant. So this means that this equation is equal to 0. I should have no sulfur left over at the end of my reaction because all of it has gotten used up. So we can set this equation equal to 0. For my carbon, I started with this many moles of carbon, and I've lost some amount of that carbon in the equation. What is x? We're going to have to solve for that in a minute. So this one we're just leaving as is, no equal sign. Okay, then at the end, I had 0 plus x for my carbon disulfide, so I'm left over with x amount of carbon disulfide at the end. So we know that this thing is our limiting reactant, therefore completely consumed. That's why we can make it equal to 0. So to solve this for x, how much we're losing, we just write out our equation, 0.9747 minus 2x is equal to 0. However, you actually already solved this because we had to a little bit earlier. When we rearrange this equation, we end up with 0.9747 is equal to positive 2x, divide both sides by 2, and you end up with x is equal to 0.9747 divided by 2, which you did up here. So if your mole ratio is not 1-to-1, you're actually already going to do a little bit of the work in step 3. So we know what x is equal to because this is how many moles of sulfur are getting consumed in the reaction, which you already did above. So this tells us that x is equal to 0.48735 moles. This is how many moles of sulfur get used up in this reaction. So now we can take x and plug it back in to solve for any other unknown quantity. But you also have to keep in mind, what am I asking you to solve for in this problem? So in this problem, I only really care about the mass of carbon disulfide that I'm producing at the end. So if I know that I have x moles of carbon disulfide, x is equal to 0.48375 moles. So that tells me that this is the amount of carbon disulfide that I had, because x is equal to the amount of moles after. But I don't want to end with moles, I want to end with mass. So the very last step to solve this problem is to convert the moles of carbon disulfide to mass of carbon disulfide. So how do we convert between moles and mass? Molar mass. So you're going to take your 0.48375 moles of CS2. You're going to multiply it by the molar mass over 1 mole, and you're going to end up with some amount of carbon disulfide at the end. I will leave you to do that last step on your own. You can check in with the answer key when you're finished, but you should end up with some mass of carbon disulfide.